Okay, so let's start. We were discussing about noise and more specifically thermal noise and its effect on your overall circuit performance, right? So with that, wherever we stopped last time was we were discussing the effect of signal to noise ratio when we talk about noise in a simple transistor. And till now, we kind of considered noise from the gate resistance and the noise from the channel of the MOSFET. We also modeled this noise in the resistance as a series voltage source of having certain power spectral density, and the noise from the channel as a parallel current source having certain power spectral density. Okay, and then we found out the total current here, the signal current and the noise current, and we did the ratio and we found out some SNR, right? Signal to noise ratio. The other part that, and the conclusion from that was that if I neglect that noise from RG, which is kind of in our control because we can make RG as small as we can, as we want it to be by simply putting transistors in parallel, right? That is essentially the gate routing resistance. We can bring it down. So if that is the case, then the noise of the channel will be the dominant one because IN is directly proportional. Power spectral density of IN is directly proportional to GM, right? It doesn't matter how you make the transistor; it is proportional to GM. If you have to realize certain amount of GM, that amount of noise is going to come. There is no amount of playing around with geometry that's going to help. So if that is fundamental, that is fundamental to a circuit, then you cannot really you cannot do any geometrical change or material change or any change for that matter to reduce noise. However, we are not only interested in noise, we are interested in signal to noise ratio, right? If we cannot reduce noise individually, we have to see if we can increase the signal to noise ratio. Fortunately, we saw that the noise power is proportional to GM, but signal voltage or signal current is proportional to GM, which means the signal power is proportional to GM squared, right? So the signal to noise ratio thus is proportional to GM. So that's a good thing because now I have a handle to increase signal to noise ratio if I want, even in the presence of noise, right? So if there is something good that is happening and something bad that is happening, we just have to ensure that the rate at which the good increases is much better than the rate at which the bad increases, right? So then the ratio becomes favorable in our favor, right? So that's what this is. Another important aspect that you need to be mindful of is in the presence of channel length modulation, we model the transistor in saturation like this, right? This is if this is GMVGS, and this is RDS or GDS. The part that you should be mindful of is to note that even though this RDS is a resistor, this RDS does not contribute to any noise because this RDS is a modeled resistor. This is not a physical resistor, right? The source of noise is the channel underneath the oxide, which has charges, right? So that in the presence of physical charges and the random motion of the charges due to thermal fluctuations, you get some noise. You don't get noise because of some small signal resistance. Okay, so this RDS does not contribute to noise. In this model, you do not replace RDS with, when you do not add another noise source in parallel to RDS, modeling the noise of RDS. So that you should not do. Okay, okay, fine. So now going forward, let's do a couple of things. One is very often you are going to see a transistor noise being modeled in some fashion, right? So you will understand when I talk about what I mean by that, hopefully by end of today's class. So, but before going there, what I would like to do is have a Norton or a Thevenin equivalent of a transistor in the presence of a noise, right? So this is the Thevenin equivalent or Norton's equivalent of a transistor in the absence of noise, right? So if I have to include noise, and let's say I'm neglecting the noise from RG. If I neglect the noise from RG and I want to modify this, what should I, how should I modify this? And I want to include noise in this model, right? So I should have a current source. I should have a current source. Direction doesn't matter because you can have it in any direction because it's noise. And I understand this is some IN, right? The only thing that we know is the power spectral density of IN is 4 KT gamma GM, right? Okay. So very often this is also modeled like this. This is equivalent to saying I can model it like an OTA of value GM. This should be negative direction. And this is RDS. And there is a current source, noise current source IN. This is the VGS, right? This is one model that you are going to see very often because just to make the circuit representation compact. The other very popular way of representing this is make a Thevenin equivalent of this. So this is the Norton equivalent. So if we want to make a Thevenin equivalent, so if I have to make a Thevenin equivalent, what do I see? So if I have a Thevenin equivalent, what will I replace it with? Yeah, and the value of the voltage source will be, right? So the voltage source, value of this voltage source would be, by the way, I should not put this right now. So I'll have a voltage source and some resistance in series. And in the absence of noise, I can, what will the value of the voltage source? And direction? Minus, right? So it should be minus GM-VGS, RDS, right? This will be RDS. Now, in the presence of IN, how will that manifest itself? So by the way, I am talking about these two terminals, right? I'm talking about Thevenizing between these two terminals. So what will, so now, yeah, so so it will be a voltage, I mean, what will be the value of the voltage source that will come in series in the presence of noise? IN RDS, right? So it will be IN RDS, or small RDS. And this will be your output. So this is often again represented like a shorthand is, let's say that. Okay, so this becomes, so this is the common terminal here, right? If I call this AB, this will be AB. So now, again, I mean, even though it's obvious, it is important for me to mention that in both this configuration and this configuration, so this is A, which is equal to minus GM VGS RDS. this guy is noiseless. And the top guy here, this is also noiseless. Because we have taken the noise, we have modeled the noisy, we have modeled the noisy OTA or the noisy voltage control current source or the noisy transistor as a summation of one noiseless voltage control current source or a voltage control voltage source plus some additional noise source. That does not mean that in principle I would be able to separate these two, right? It's essentially I mean, just because I have written this, it doesn't mean that you can say that I will separate this out in physical reality and get a noiseless device. That you are not going to get. This is just a model, right? So in your model, this entire thing is a device. Okay, so that is something that you need to keep in mind. Okay, fine. So this type of representation often, the noise representation of this is often referred to as an output referred noise. So this is represented as, this is representation noisy device as a noiseless device plus noise source or the output referred noise source. Okay, so similarly, later on in this class, you will see that there is ways of, moment I say something is output referred, which means there is an option of making something input referred also, right? You'll see later on, later in today's class, how do we do that? Okay, fine. So this type of modeling is important. It helps us to achieve certain things, right? So the next part, the next 10 minutes, we'll look into why this type of modeling is helpful. So let's dive into that part. So let's say I again start off with a common source amplifier, right? So this is a very good dummy example for everything. And I'm not showing biasing. So now let's say I have a RD here. So in the previous examples, we didn't have RD. Let's say VI. And this is my V0. I want to find out what is the signal to noise ratio at between V0 and Vi, right? Basically, I want to find out the signal to noise ratio at V0. Okay. So how should I go about doing it? Yeah. So firstly, when I say that I want signal to noise ratio, which means I need the signal, I need to do an analysis for the signal. And the second step, I need to do the same analysis for noise, right? And then take the ratio of power, right? So signal is well known in this case. I will not draw the small signal, right? So basically, V out sig is minus, tell me, GM RD times VI, right? So essentially your pass spectral density of your signal is V out signal will be GM squared RD squared is V in. Okay. Now let's do the noise part, right? So how should I replace whatever we have till now with the noise model? So I can either replace this thing with the noise model that we just saw, or we can, since it's a simple circuit, I can as well replace this with the incremental equivalent that we are familiar with, right? So let's do that first. Then in the later stage of this course, we will start replacing them with the model. So this is the transistor model, and I'm neglecting channel in modulation. So this is GMVI. And I have additional noise sources. I have a noise source here, IN1, and I will model this RD and the noise source due to RD as RD and a voltage source VNR. Okay. Power spectral density of IN1 and VNR are known to us, right? So now the question is, what do I do with this GMVI? For noise analysis? What does it mean? And when we say we don't consider means what? We can neglect. Why can we neglect? Because VI is essentially zero, right? We are doing superposition of two analyses. So this goes to zero. This goes off. So your V out or rather VN out, I should write, because I'm doing noise analysis. VN out is essentially superposition of two cases now. So IN1 times RD should be negative because the other way around, but shouldn't matter in the end. Plus how much? VNR, right? VNR. Which essentially means that your SN out, the total noise at the output, is SIN1 times RD squared plus SNR, right? Okay, so this is 4 KT comma GM RD squared plus 4 KT RD. Okay. So what is your SNR? Signal is GM square RT square times SV in. Noise is 4 KT. I'll just take 4 KT common. GM RD squared plus RD. Right? Okay. So from this, if I simply say that, what should I mean, so this part, if I just concentrate on this part, this is the part that is familiar to us because that is the one that we did in the earlier class, right? But what is this extra part? Why does this extra part come? Noise of the resistor, right? So now tell me, what do you want the noise from this resistor to be? You want to be very high or very low? Very high, right? So what do you want this RD to be then? Very high or very low? I want the SNR to increase, yeah. Yeah, right? So if SNR has to increase, then RD has to go low, right? Yeah, right. So why does it make sense? Pardon? The noise associated with the resistor. So value of resistance increases, the noise equivalent is also. Okay, so let's see, right? So why do you say so maybe we can recast this in certain ways so that it makes sense, right? So this is equal to, so because there are so many terms of RD, so I will isolate RD, right? So let's say I divide everything by RD square, right? So let's say I divide everything by GM square RD. Okay, GM square RD, I can divide everything by RD square. Or maybe I can divide everything by GM square by RD square, because then I can isolate the SV in on the top, right? So let's do that. So this is SV in by 4 KT. This is 1 over GM by 1 over GM squared RD, right? So I'll write as GM times GM RD. Right? So again, you cannot do anything about this part, because that anyway, the GM is a requirement that will come. So now tell me, what should I do to maximize SNR? With regards to RD, what do I need to do? No, let's say I am not wanting to touch GM. So what do I need to do? I need to increase or decrease RD? Increase RD, right? I want to maximize this ratio, so minimize the denominator. I would like ideally the RD to be infinite, right? I want ideally the RD to go to infinite. So in that case, I'll get maximum SNR. So now, do you see any issue with this, in the sense that, so before in the sense that what I essentially told in the previous class was, in order to increase SNR, you have to increase GM, right? So again, I have a GM here and I have a RD here. So in order to increase SNR, you have to increase GM to increase SNR. But now I am saying that, note that GM and RD have different, one is a conductance, transconductance, other is resistance, right? They are of different, they don't go in the same direction, basically, right? They are different properties. So wouldn't it be intuitive to say that if I am increasing GM in the bottom, in the transistor to increase SNR, shouldn't have I increased the conductance of RD to increase SNR? Yeah, so it's going in the opposite direction, right? So so let me take a step back, right? Let me take a step back and model this RD noise in a different way. Then maybe the point that I'm trying to make will get across. Yeah, so that's what I mean, let me model it in that way. That probably will be more helpful in understanding. So what I am trying to get at here is that we have modeled the noise of the resistor as a voltage source in series of value Vn. So I could have as well modeled this as a current source in parallel and of value Vn by R, and this is R. And what would have been the sparse spectral density of this current noise? It would have been the sparse spectral density of Vn divided by R squared, right? So I should say SVR, SV or SIR, the noise current. SIR would have been SVNR divided by R squared, that is 4 KT over R, that is 4 KT G. Correct? So essentially what I'm saying is, I have a noise current source from here, that is 4 KT gamma GM. I have a noise current source from top, that is 4 KT G. I am saying that in order to increase SNR, I have to increase GM, but I have to decrease G. Right? That's what I'm saying. So why does it make sense? Okay, math turns out to be agreed, but intuitively, why does it make sense? So increasing GM increases signal power also, but increasing G does not have any effect on signal power. right? Because the signal is flowing. What is the route of the signal? The route of the signal is this. It only flows through M, the transistor. The signal doesn't flow through the resistor. The resistor is there just to bias and give high impedance, right? So what is the key takeaway? You need to increase the strength of the signal path. If there is no signal flowing through any path, and if you keep increasing that strength, you are going to incur more noise, right? So identify when you have when you have bigger blocks, right? Multi-transistor configurations with multiple biasing, this and that, and you are asked to increase SNR, you have to identify which path is the signal path, and then increase the strength of that signal path. I mean, that increasing strength might be increasing the GM or increasing some R, I don't know. It depends on the configuration, right? So increase the strength of the signal path and decrease the strength of everything else. That would give you good noise performance. If you simply go by the adage that increase GM to decrease noise, then you'll end up in trouble because, for example, and I'll give you another example. Let's say I can as well replace this RD with a active load, right? I can use a P MOSFET. So let's say I use a P MOSFET. And this is incrementally grounded. So the noise current through this is for, let's say, call it M1, M2. 4 KT, or rather, I should say SV M2. G and M2 is 4 KT gamma GM2. And SV and M1 is 4 KT gamma GM1. And I ask you to find out the SNR. You are going to get some value. But you know that it has been taught in class to increase GM, to reduce, to increase SNR. So you increase GM for both. So will it help? It will clearly not help because the noise is, the signal is only going through M1, but the noise is getting contributed both by M2 and M1, right? So you have to identify what is the noise path, what is the signal path, and they need not necessarily be the same all the time. In fact, they are never the same. Signal path is only a subset of the noise path, right? So you'll have to, meaning you have to increase the strength of the signal path and reduce the strength of the noise path. Now that is not always very straightforward to do because you are going to face, I mean, for example, if I go back to this common source amplifier case, what is essentially saying is that if I have to increase noise, if I have to increase SNR, I have to increase RD. Reduce means increase RD. And that obviously you cannot do indefinitely. Why? Yeah, biasing issue, right? You will not be able to do. There is a maximum limit you can do, right? So that limit will essentially set your noise performance. Okay, fine. So that is important thing to mention. Take a note. So I'll also make a note of it. To increase SNR, increase the strength of the signal path, and reduce the strength.
So what do you mean by strength of the signal path?
I'll define strength of the noise path. If possible, sometimes it is not possible, you have to live with it, right? So when I say, his question is, what do I mean by the strength? In this, now the definition of strength can differ based on context. In this context, what is meant by strength? It is meant by, ideally, it's basically the power, right? The power contribution, or when you ultimately look at the output, you are going to get an expression of power. In that expression of power, you will see that the signal has certain proportionally constants. So you increase those proportionally constants. So that those proportionally constants will come through will be the GM of some transistor, right? So essentially you increase the GM of those transistors. And the denominator in the noise, you are going to find the same same guys will appear in the denominator also, but additionally, you are going to find some other terms. So those terms are there in the denominator and not in the numerator because they are attributed to noise and not to signal, right? So when I say strength, it can be the gain, it can be transconductance, it can be whatever that particular configuration is, right? So strength is essentially a very generic way of talking about it, but it depends from configuration to configuration. In this particular example, essentially the strength refers to GM. Right? Strength of the noise path, signal path is GM. Strength of the noise path is both GM and RD. Right? Both are contributing. You cannot do anything about GM for noise because that also comes in the signal. Right? But that's okay because if you keep increasing GM, the signal path SNR is in your favor. It keeps on increasing. But the noise path only adds noise, no signal. So you have to make sure that that is as low as possible. Okay? Fine. Any questions so far? Okay. So then let's go to the next part. That is what happens if I cascade multiple blocks, right? It's often because when you design it in the RF chain also you have seen there are multiple things which comes in cascade. So there will be noise contribution from each of them. How does it help or doesn't or distort the final performance? So let's do that. So let's say I have now what I'm going to do, I'm going to use a model that we developed, either Thevenin equivalent or the Norton's equivalent. Let's go with the Thevenin equivalent. So let's say I have one amplifier, A1. There is Vn1 is the noise. It has some resistance. Then you have another amplifier of gain A2. And let's say this is R1. You add some noise, Vn2. There's some resistance R2. And you get some final output V0, right? Okay. For the time being, I'm assuming that these input resistances are infinite. Right? For simplified analysis. So I need to find out what is the signal to noise ratio at the output and then try to see if we get some intuitions. Okay. So if I have to find out the signal strength at the output, what will it be? So SV out will essentially be how much? Right. Yeah. So essentially, exactly, right? So again, we can use superposition. So in that case, I can essentially null the noise sources, right? So the V out is essentially Vi times A1 times A2. So your SV out is SV in times A1, A2 whole square, right? And what is SN out, total noise output? So in that case, I will null Vi, right? So I will null Vi, this goes. So essentially this node is 0, right? Now Vn1 and Vn2 are appearing, right? I can as well do them individually, but simple circuit, I'm going to do it together. So this node is now, this is 0, this becomes Vn1. So this becomes A2 times Vn1. So this becomes A2 times Vn1 plus Vn2, which is essentially your output, right? So what is Sn out then? Your SVN1 times A2 squared, right? So this is essentially A2 squared times VNN1 squared, that is SVN1 squared, plus SVN2, right? So note that the first stage noise at the output of the first stage goes through an amplification. The second stage does not because there is no amplifier following it. Okay. So what is your SNR then? SV in A1, A2 squared divided by SVN1 squared by SVN2, right? So I can as well divide by, let's say, A1, A2 squared. Right? So I get SV in by SVN1. Let's say I divide by A2 squared only. A1 squared, because A1 squared anyway will be common. Mistake, right? Should be A2 squared, right? Huh. Okay. So now, what intuition do you get from this expression? Or before getting intuition, do you see anything interesting in this expression that is of any design interest? Again, the goal is to increase SNR. And you can assume that A1 and A2 are of similar values. And VN1, SVN1 and SVN2 are of similar values, similar strengths. Because they are ultimately made up of same type of devices. And they will be probably not be factor of 10 apart. Pardon? Which one? There are two stages, A1 and A2. Okay. So, or in other words, if I flip the question and ask, which stage, given that A1 and A2 are similar, SVN1 and SVN2 are similar, which stage contributes to the most amount of noise at the output? First stage, right? Is that evident to everybody? Okay. So what is the intuition? Why does first stage contribute to most amount of noise at the output, given that if all the stages have similar noise contribution individually? Yeah, but intuitively, can you see why it is? Yeah, so that is one way of talking about it, that it also follows a signal path. But I think the more intuitive way of thinking about it is this. So you have, let's say you have a signal. The signal gets amplified by some factor, let's say factor of 2 at A1. So it goes up by this. And then again, a factor of 2 at A2. So it kind of increases here. The VN1, let's say, is small wiggle, something like this. Right? It goes up by a factor of 2 at the output of A2. So VN1, VN2 basically goes something like this. And VN2 is also of the same strength, but it doesn't go through amplification. Right? So VN2 will be something like this. Right? So at the output, because the first noise of the first stage gets amplified, it appears to be the dominant noise at the output, right? So if I flip the argument around, what I will say is that the second stage does not contribute to any significant noise at the output, right? The most of the noise is contributed by the first stage, because the noise that is getting accumulated at the input of the first stage goes through multiple stages of amplification. In this case, one stage of amplification, but if you have 3, 4, then it goes through multiple stages of amplification. Does that make sense? Right? So what is the design benefit of this? Fine, math tells us this. The design benefit of this is, in general, what is the trade-off between noise and power, SNR and power? Take the example of common source amplifier. You need to increase power to increase the SNR, right? So you have to increase GM. But let's say power is of interest. Obviously, power is of interest. And I see that A2 noise is not the dominant noise. Then do I need to size A2 for very good SNR? I don't need to, right? I can reduce power in A2 because anyway A2's noise is not being the dominant noise at the output. Right? I can reduce the size of A2, rather I reduce the size GM of A2, and to ensure that the output noise is not the dominant one. Right? Does that make sense? Right? So that will help you save a lot of power in your design. Okay? No, not A2 itself. You want, so firstly, the gains when you size gain, size gain because you want to amplify the signal to some extent, right? So once the gain is fixed, right, you don't want to tamper with the value of gain. Now, how can you, there are multiple ways of achieving the same gain, right? For example, in a common source amplifier, the gain is GM times RD. So to achieve the same GM times RD, I can either increase GM, reduce R, reduce GM, increase R, right? So now both of them, even though gives the same gain, they have different power consequences. If I increase GM and reduce R, naturally I'm consuming more power, right? But increasing GM, reducing R, I would like to do if the noise contribution of that stage is critical. If that is not critical, I would rather reduce GM, increase R, right? Noise is not much of a problem, and I'm saving power also, right? Does that make sense? Some of you seem confused, right? So again, let me go back to this example. This common source amplifier scenario. If I have to, this is the only isolated case. I want to increase the SNR of this case, of this configuration, without changing the gain, right? That is GM times RD remains same. I want to reduce signal to increase signal to noise ratio. What should I do? Increase GM, reduce R, right? If I do not want to tamper with the gain, right? So if I increase GM, reduce R, naturally I'm going to consume more power, right? Another way of thinking about it is, if let's say I increase, so I have this configuration, RD, and this gives GM. I want to increase GM by a factor of 2 and reduce R by a factor of 2, right? What is the most intuitive way of doing it? I can take this circuit, copy it, put them in parallel, right? So I can simply copy it, put them in parallel, right? So effective GM goes up by a factor of 2, effective R goes down by a factor of 2, your effective power consumption goes up by a factor of 2, your effective SNR increases by a factor of 2, right? Your SNR is essentially, I mean, you look at this or look at this expression, right? So all you are doing is you are keeping GMR same, and you are changing GM, increasing GM by a factor of 2. So naturally SNR also increases by a factor of 2, but at the expense of power, right? So that is why sometimes when you see that I have certain amount of SNR, and that is not beating the spec, I am factor of 4 away. Power is not too much of a concern. You just basically copy the circuit 4 times, put them in parallel, automatically your SNR is going to increase, but at the cost of power, right? So that is why increasing noise just by putting in parallel is a very well accepted practice, provided power is not much of a concern. If power is a lot of concern, that is not an acceptable practice. So that is why often you will see that most figure of merit, by figure of merit, I essentially mean that how good a circuit topology functions is in terms of noise is often referred to as SNR divided by power, right? Because we know we can buy power using SNR, or rather buy SNR using power, right? We can pay power and get SNR, right? That there's no innovation there. We can always do that. Okay. Yes.
The topology which we have seen on the 2 stages.
Yes.
Can't we say that it is the second stage that is causing more noise, because the first stage noise is noise, VN1, but that is amplifying that VN1.
Yes.
So why can't we say that it is the second stage that is giving us more noise, because that is only amplifying my VN1. VN1, but that is amplifying my VN1 and we are getting a power.
Okay, so if I rephrase your question, are you essentially saying that, let's say second stage does not give any noise, VN2 is 0. Let's say VN2 is 0. would you still say that second stage is causing the most noise?
No, that my question is that A2 is, it has some gain.
Right,
That is amplifying BN1.
right.
So the second stage is amplifying the first stage noise. So can't we say that it is the second stage which is amplifying our first stage noise?
You can say that, but it is also amplifying the signal also, right? So the signal to noise is not getting affected that way, right? So because it is also the noise is also getting amplified by same factor as the signal. So the signal to noise ratio of the chain is not getting affected because of the gain of A2, right? But A2 also gives some noise, so that adds up the noise to some extent.
The rate of output thing is.
Yeah, exactly, right? That's all, right? But all you have to ensure is that the noise of A2 is insignificant with respect to the noise that is coming through after amplification, right? So if now the flip side to the question is, let's take some numbers, right? So let's say after amplification of, and let's say we do not consider the noise of A2 at all. After amplification, I see that I get 1 millivolt of noise at the output, right? And with VN2 in picture, I maybe get another 10 microvolt additional. So 10 microvolt is nothing with respect to 1 millivolt, right? I can as well say that A2 is not contributing to any noise. But if let's say A2 power is like 50% of my signal chain power, then I can say that why this guy is not contributing to any noise anyhow, why should I want more power there? I can reduce power, and maybe that I am okay with 10 millivolt, 10 microvolt being going to 50 microvolt. Fine, let it be. But I can kill the power of A2 by doing that, right?
So A1 is only amplifying the signal only. It's not actually, you're saying only this way.
A1 is amplifying signal only, yes, yes.
So the noise contribution coming from the VN1 that is getting added after the amplification has happened.
Yes.
So A2 is kind of amplifying this as well as signal as well as the noise.
Yes.
So, but if we can move the VN1 at the starting of if it is at the input of the A1, then we can say A1 is actually amplified both of them.
Right, but in that case, VN1 will not be VN1, it will be something else. That's an input referred noise, right? So we'll see that, right? We'll see that next, right? Okay, fine. Fine. Any questions so far? Yes.
Follow-up question for why we want to amplify the noise, but we don't want like higher noise at the output.
Yeah.
So why do we do it like before A1?
So again, we don't want to amplify noise, but this is not my choice, right? It comes with the device. This is only a model. I am not adding any extra noise here. This is the transistor model itself. You cannot do anything with the box. You put that, his point is, so let me, since the discussion came up, so let me also refer to this. So let's say I have one amplifier, A1, and this gives noise of VN1, and let's say one stage, right? Again, the assumption is input impedance is infinite, right? This is V0, this is Vi. If I only am interested in figuring out the noise performance, I don't need Vi. I can just simply ground it. So what will be output? V0 will be equal to VN1, right? Now, again, the important thing to note is that this VN1 does not sit outside the amplifier. It comes from inside, right? So right now I have modeled this saying that this guy is noiseless. And I have stripped the noise component from inside the amplifier, and for my analysis benefit, I put it outside. Now I can put it at the output, I can put at the input also, right? But what is, if I move the noise source from different parts of the signal chain, what do I need to ensure? What does not change? The total noise transfer function should not change. When I say noise transfer function, essentially mean that the total output noise should not change, because that is coming from the device. How I model is up to me, but I have to be accurate in the modeling. Just because I didn't take something into account, the noise change, that's not a right thing to say, right? So I can as well say that I will add a noise source VN1 in, this is called input referred, and say that this is A1 and this is V0, and this should be, the value of VN1 in ref should be such that V0 is exactly equal to VN1. So what will be the value of VN1 in ref? Yeah, right. So VN1 in ref has to be equal to VN1 by A1. Right. So what will be the pass spectral density of VN1 the in ref? So that is SVN1 in ref will be how much? SVN1 divided by A1 squared. Right. So this is often called the input referred noise. Right. It does not mean that you suddenly have a noise source at the input. It is our model. Right. We are modeling it as for our benefit as an input referred noise source, and this guy is noiseless.
The input referred noise is not relevant to the noise due to the input side. Like external noise is coming because of the preceding state.
Yeah. This is the property of your device. Yeah, it doesn't take into account anything that comes from here. Nothing, right? So nothing from here. This is a part of the device. We are modeling the noise of the device. Right? Yes.
Like, I mean, along the similar lines to the input referred, like if you look at the SNR equation, it seems like that we are taking the ratio at the input of A2 itself first. A1 times SV1, SV gets amplified, and then you have noise to VN1, and like VN2 gets de-amplified by A2.
Yeah. So what Dhruv is pointing out, I can as well find out why only find out the input referred noise of A1. I can as well find out the input referred noise of the entire signal chain. Right? What do I need to do? I need to find out the total noise and divide by the gain of the entire signal chain. Right? So we can as well do that in this case. Right? So if I have to find out here, so what is VN? So your VN out is essentially VN1 times A2 plus VN2. And if I refer it to the input, right? So essentially what I'm saying is that I'm trying to do this. I'm trying to say that I am going to add some noise voltage source where this guy is noiseless, but the total noise at the output remains whatever it is supposed to be. So what will this V input referred be? This will be Vn out divided by A1, A2, right? Because this guy is V in ref times A1, A2, right? And that has to be same as Vn out, right? So essentially this becomes this Vn1, A2 plus Vn2 by A1, A2, which means that SV in ref becomes SVN1 by A1 squared plus SVN2 by A1, A2 whole squared, right? So if you think of your signal chain as a noiseless signal chain, and you want to model this signal chain along with noise, you can as well say that you can do it one of two ways. You can say that this is the signal chain which gives so much of amplification, and after amplification, if you observe the output, this is the amount of noise, right? That is an output referred way of modeling the noise. Alternatively, you can say that I will say that this signal chain gives me this much amount of amplification, but you can assume that the signal chain also comes with a noise source at the input, which is a modeled noise source, and the value of the noise source is this. Again, it's a modeling thing. It's not a device thing, right? It's a modeling thing. Okay. So now from this model, so why is this? This is one of the most preferred way of representing noise models, because it also gives you a lot of intuition. What intuition does it give you? It essentially tells you that the noise of the second stage is getting input referred noise of the second stage is getting de-amplified by the gain of the entire signal chain. But the noise of the first stage is only getting de-amplified by, or rather attenuated by, the factor of only the first stage. So again, which is the dominant noise contributor? First stage, naturally, right? So if A1 and A2 are of the same order, SDN1 and SDN2 are of the same order, you can as well approximate this guy as saying that second stage is noiseless. Only the noise contribution comes from SV from the first stage, right? So that is why the first stage of your signal chain becomes very critical in determining the noise performance of your entire circuit. And that is why the first stage of your RF receiver is also called a low noise amplifier, because you have to ensure that its noise performance is extremely good. Otherwise, you are going to deteriorate the noise performance of the rest of the signal chain. Okay. Any other questions? Yes.
What if A2 instead of another amplifier, it's like buffer, which is A2 is slightly less than 1.
Right. So he's attenuator, let's say. It deteriorates. So what happens if A2, that's a good question. What happens if A2 deteriorates? So in that case, we'll do an exercise in the next class. If intuitively, what do you think? Let's say A2 adds the same amount of noise, but it reduces the signal. What's going to happen? SNR is going to go down, right? So you are adding same amount of noise, but you are reducing signal. It's going the other direction, right? You are basically, if I mean, it comes out from this also, right? If A2 is less than 1, the denominator gets dominated by, it can potentially get dominated by that, right? So sometimes you require attenuation. Should be intuitive now. If I give you an example, let's say you are working in an environment where there is a lot of blockers, very high swing blockers, and you want to bring it down to a certain level, and filtering is simply not helping. So you kind of attenuate your signal to some extent and then process. But in that way, you also incur noise. A practical example of that is, let's say you are receiving a phone call. The next tower is 1 kilometer away. You probably have 1 bar in your cell phone. You're barely able to hear, because the signal strength is very small, right? So your LNAs and everything are at maximum gain, right? They're operating to amplify the signal down the signal chain. Now you start moving towards the tower, right? So the bars increase and you go very close, it becomes 4. Then obviously the input signal strength has really increased now. If the LNAs operate with the same amount of gain, then you are going to saturate the signal strength, the streams down the line, right? So for example, if you go from minus 90 dBm input power to minus 50 dBm input power, that itself increases the input strength by 40 dB, right? If the input strength increases by 40 dB and you don't do anything to the gain stage later on, you are going, your device is going to saturate, right? So that is why they are inbuilt in all handheld devices. You have some programmable attenuators. It checks it finds out the signal strength and also triggers whether I need to attenuate the signal to save the signal strength down the line, buffers down the line. But it does so by adding noise because of this. But it's not a problem because your signal is already high, right? So it's not necessary that you need to always have very low noise solutions. If you know the signal strength is high, let there be some noise. Right? If the signal strength is low, then only I have to worry about noise, right? Okay, fine. Yes. Yeah. You should get the same value. Otherwise, there's some calculation mistake. I didn't understand this. Why do you say? Can you say the question again? Maybe I didn't hear properly. You are the normal thing that we have done till now is having everything at the output, SNR at the output. Now you are talking about SNR input. Okay. Why do you say so? Referred noise power the input. Are you talking about the noise power that is coming from somewhere else? Are you talking about the source noise? No, we have not taken into account source noise here. Source noise is an important factor that we'll come to in the next class, but we have not taken source noise into account at all. Right? All we are saying is that the source is noiseless, right? And we say the SNR at the input. There is a definition issue here. The way we are saying is, I should say that the input referred SNR, not the SNR at the input, right? Because that is at the input of your device, there is no noise. The noise will come only when you go through the device, right? Right. So if after the signal traverses through the device, you are going to get a noise. Before it goes, there is no noise. But this noise definition is a referred noise, right? We are referring for the mathematical purposes, and we are saying that the input referred SNR, not input SNR. Okay, input SNR means that the signal to noise ratio that the signal that is coming in is bringing along with itself. Okay. So is this question clear? That's the important question actually. Okay. Okay. Any other questions? Model is applicable for only this. Yeah, right. I mean, that stage as in whatever you have modeled for. If you have modeled for the entire chain, model is applicable for the chain. If you model for only one stage, it is applicable for the stage. Yeah. Basically, we are moving around the signal just to ensure that, but you have to, holy grail, you have to ensure that the output doesn't change. Right? You do whatever you want in your circuit. If the output changes, then there is something wrong in whatever you're doing. Right? You ensure that the output doesn't change and you move things around. I mean, till the end of time, there is no problem. Right? Okay, fine. So since we are considering this input referred stuff, so there is an important aspect that you need to be aware of. Here I have conveniently assumed that your input resistance of your amplifier is infinite. Okay, but if it's not infinite, there is an issue. The issue is it's not very apparent if you do not think about it. Well, let's take this into account. Let's say the input is so there is an input resistance. Let's say there is an input resistance to your amplifier. Okay, and I'm input referring the noise voltage source, right? So let's say this is V in ref, right? So this is input referred noise of this amplifier A. Okay, and let's say this is the input of this. I'll take an extreme example. Let's say the input to this guy is a current source, right? So this. Let me mark it in a different way. This is input referred, and this is an actual current source, some V in. Okay. Extreme case, all current sources have our output resistance. We'll generalize later, but let's say I model it like this. This is I in. Signal current. Okay. So what do you think will be the output noise in this case? In this model? RM is a modeled input resistance, right? So all the noise I have encapsulated in V in ref, right? So that's this guy is noiseless. So that's the meaning of referring a noise, right? You are stripping the noise out of the device or the amplifier. So what will be the noise at the output? Why? What are you going to do to find the noise at the output? You are going to open the current source. If you open the current source, what will be the resistance across, what will the voltage across iron? There is no current through Rin, right? If there is no current through Rin, what is the voltage drop across Rin? 0. So what is the output noise? 0, right? So you have magically now found out a way of reducing noise. Is this correct? So what is wrong? So firstly, intuitively, should we have output noise? Of course you are going to have, because it's a property of the device. We are playing around where I want to put the noise source in the model, right? So what is wrong?
They are not considering the resistance in parallel to the current source.
We can consider, and let's assume that this resistance is much higher than Rin. That is a practical thing that can happen. It's the same thing, right? Instead of getting 0, you're going to get a lower noise. But that's also not accurate, right?
So that is like the voltage of static, right?
Yeah, sure. I mean, basically you are saying R out of this input current. Sure. I mean, if I say R out is much, much greater than R in, right? So this V in ref, what's going to happen? I mean, it's not going to cause, I mean, the overall it will have a resistive divider between R in and R out, right? The V in ref will have a resistive divider between R in and R out. And if R out is much, much greater than R in, essentially you are saying the output noise is a much attenuated version, right? But with that, I mean, are you then saying that actually the output noise will attenuate because I have done something at the input?
That's kind of modeling, right?
Yeah, so what is, you have to increase the input referred noise by a factor. That I agree, right? To some, what he is essentially saying is that then I have to be cognizant about. So looks like if an extreme case is, okay, let's take this example. If I model this R out of the input, then what is the voltage across this? This is V in ref times approximately R in by R out, if R out is much greater than R in, right? So looks like, and then finally noise will be this times A squared, right? So it's still an attenuated factor. What Abhay is pointing out is that just take that attenuation factor into account and increase this guy by this factor. That will work. That is going to work, no issues. But the practical problem is, when you are selling your device, you don't know who is going to use it and what is the R out, right? If the next stage is for you are designing, fine, you can do this. But that becomes a problem of what you are interfacing at the input side, and that need not necessarily be in your control. So we need another model, basically, which is independent of whatever you are connecting here. You can connect a voltage source, current source, has a resistance, doesn't have a resistance. You should have a model which essentially is able to mimic what the noise performance of your signal chain will be without bothering about what is getting connected at the input. And it will be accurate under all circumstances. That should be the requirement, right? And yeah, so essentially the issue is now current is not passing. That's the problem, right? So if I simply modeled it as a voltage source at the input, I could have as well modeled it as a current source at the input. There's no stopping us from modeling it as a current source, right? I could have as well said, this is I in ref, right? So in this case, if I model provided I in ref is taken care in the modeling so that final output noise is fine. So in this case, it's not a problem. This I in ref has a path to flow into RDN. It will generate a signal, and you are going to generate a noise at the input, and you are going to get an output, right? So that solves the problem. But does that mean that instead of modeling your input referred as a voltage source, I model it as a current source, it will solve all problems? You need to use both, because now let's say instead of I in becoming a voltage source, a current source, it becomes a voltage source, then you have the other problem. Because current and voltage are dual, right? So essentially the solution is you need to, when you are input referring a voltage, input referring a noise, you need to have a model which has both. And this becomes your noise model. So this is the one that you can give to your customer, and he or she can drive whatever he or she wants, and it will not break the model. Okay. In typical analog circuit design, you will not see this I in ref to be modeled, because in most cases your Rin is capacitive at frequencies that you are interested in. They are much higher than the output. I mean, you can assume that they are infinity. Right? If Rin is infinity, then the requirement of I in ref doesn't appear. Right? Because if Rin is infinity, then having a modeling it with a voltage source itself is fine, right? So let me also write that down. If Rin is infinity, then having this solves the problem in almost all cases. Because, I mean, ultimately you are never going to drive anything with the ideal current source. There is going to be a resistance. And since no current can ever flow into it, so input referred voltage is good enough in most analog circuit applications, which does not draw in current. Okay. But as it turns out, in most RF applications, input, because of matching requirements, your input resistance is almost never equal to infinity. There's some 50 ohm or fairly low, basically, not even kilo ohms. So, so you need to take into account both. Right? When you'll be doing 613, you will see that its I in ref is probably hardly ever taken into account. But in RF, it does. That does not mean that RF requires something that 613 doesn't, just that it is not required. Right? It is not in most low frequency applications. When I say low frequency, I mean sub gigahertz applications. You probably don't need to model I in ref, because the input resistance is much higher than the source resistance, right? It's basically which is higher than what. Okay, fine. Any other questions before we stop? Yes.
Even if Rin is finite, even if Rin is finite, and the input is voltage source.
If Rin is finite and the input is voltage source, okay?
That is modeling the current. The current will go to the voltage source and it will not go inside.
Yeah, right.
Even with finite input, it will work. The source is voltage.
Provided it doesn't have any input resistance.
Yes, ideally.
Right, and that never is the case. When you are talking about these applications.
Like including both the models. We need to consider like Rin, voltage source, then solve it and put one only.
No. When we are doing this, the purpose of this model is to ensure that you did not bother about what is there in the what is driving it. If you do not use this model, and if you only use either voltage source or current source, then you have to bother about what is driving it. Yes, because you need to have the information of that RS. Right? So an extension of what you are saying is, so let's say I have an amplifier. It is noisy, right? So I have output referred noise and all. And I have an input which also has a resistance RS. Okay. So I need this model for the input referred if I am trying to put this guy in a box. If I am planning to put this entire thing in a box, then I don't need, right? I can simply refer a voltage source at the input and be done with it, right? If you have the luxury to encapsulate the source resistance into your model, then only one is fine. Only V in ref is fine, because having a noise current here is immaterial, because this is going to flow through here, right? It's not going to induce any voltage. Yes. What you need to? Yeah. No. So you anyway need to know that in either case, right? So you need this Z-in information, you anyway need. That is at least a part of your device. Yeah, for the whole, if you know Z-in, the whole box is RS plus Z-in, right? So what I am saying is that this is coming from the source. And if you refer to the input of the source, then only referring a voltage source is fine. If the source is also a voltage, right? If the input is a voltage source and you refer everything to the input of the voltage source or the output of the voltage source, then only one one voltage source referring is fine, but if you are not doing that, you are referring it here, and you have neither RS is 0 nor Zin is 0 or infinite, then you need to have both, right? So that is why the noise models of an isolated system should always have both the voltage source and a current source. Okay. So we are going to do an example in the next class and take it forward. Okay. Okay. Thank you.